10.5, applications of matrices and determinants. The main point of today. Do you have a question?
No, I was
Oh, you're going to try to steal the camera?
Yeah, but I see
Okay. One objective today, and that's Cramer's rule. Back when I was taking this course, was ninth grade or whatever it was, 8th grade, I don't know. Cramer's rule was the coolest thing because I hated substitution. I hated elimination. I hated row operations. I just did. I was like, this is, huh? Well, we didn't have calculators that would do what today's calculators do. And so, I mean, how many times have y'all been solving an equation using elimination or something, and you find yourself in a loop?
Oh, once or twice.
Okay, like all of a sudden, dang it, I still have two variables. Dang it, I didn't get rid of the right one. Man, what's okay? I hated when that happened. But with Cramer's rule, boom, it was done. Determinants were easy. Down diagonals minus the up diagonals. There's your determinant, right? Huh? Stop it. Okay, so Cramer's rule is going to involve a lot of matrices. And we'll talk about it in just a second. In this section, you're going to study one more method, Cramer's rule, named after Gabriel Cramer, who lived back in the 1700s. The guy was 48 years old when he died. If he made his 48th birthday, he might have only been 47. I don't know. Uses determinants to write the solution of a system of linear equations. One of the slides that we looked at yesterday looked like this one. And I don't understand why this information was on yesterday's lesson, because this is Cramer's rule. Okay. So this system has a solution. That solution can be found by x is equal to, let's look at the denominator. What's so funny? So Brianna's back there kind of laughing, and I'm like, she's...
making noises like push it in. So it's kind of like here, every time the rotor would pause, I push it a little further.
Okay, look at the denominators on these. Both of them are exactly the same. A1, B2 minus A2, B1. What is that? What is A1, B2 minus A2, B1? It's these coefficients, right? The down minus the up. For Jacob, it's the down product minus the up product. For Nevaeh, it's the down product minus the up product. And I'm not doing it for everybody, okay? But it's the coefficients. The coefficient determinant is in the denominator. What about the numerator? They're different. What changed about them? We'll talk about it in more detail later. A1, B2 minus A2, B1 can't be 0. How come? Can't divide by 0, right? So if the determinant is 0, can we use Cramer's rule? No. It's from Cramer.
What are we supposed to use?
Okay. To solve a system.
I was listening about how he hated elimination and substitution.
And what do you use elimination and substitution for?
Finding the variable.
To solve a system.
That doesn't have x's and y's. I don't think it works that way.
Moving on. Each numerator and denominator in this solution can be expressed as a determinant as follows. So on the last slide, they had this piece and this piece given to you. What they've done is they've kind of expanded it out just to show you that the bottom is the determinant of the coefficients. The bottom is the determinant of the coefficients. What does column 1 in our matrix? What does A1 and A2 represent? The coefficients of what? Which variable? Huh? Okay. A1 and A2 represent, let's go back to the problem itself and scroll down. and come back over. We'll get there in a second. Okay, A1, we were on the right slide to begin with. Okay, A1 and A2 represent the coefficients of X, don't they? B1 and B2 represent the coefficients of Y. Y'all good with that? Okay. Now, if I want to solve for X, first of all, I want the coefficient matrix in the bottom. In the top, let's go back here. Where'd A1 and A2 go? Well, it's on the bottom on both of them. But in the top, what replaced A1 and A2?
C1 and C2.
What is C1 and C2? They were the solutions. So to solve for X, we replaced the X column with the solutions. We left the Y column alone. The bottom is simply the coefficient matrix. It doesn't change. To solve for Y, what do we do? X column stayed the same. The Y column became the solutions. Because I'm solving for Y, I'm putting the answers in the Y column. When I'm solving for X, I'm putting the answers in the X column. Okay? Easy stuff.
I don't know what I missed.
That's right. So the coefficient matrix is the A1, B1, A2, B2, right? That's the coefficient matrix. A1 and A2, that's my X coefficients. B1 and B2, those are my Y coefficients. If I want the determinant of my coefficient matrix, I call the determinant of the coefficient matrix D. No subscript. If I replace the X column with the answers, this is the determinant sub X. I use the determinant sub X to find the value of X. If I replace the Y column with the answers, I'm now going to calculate the determinant sub Y. I'm going to use the determinant sub Y to solve for Y. What does all this mean is what you're thinking, right?
Yeah.
Okay, here's an example. My equations are 2x minus 5y equals 3, negative 4x plus 3y equals 8. My coefficient matrix, 2, negative 5, negative 4, 3. Y'all good with that? First thing I want to see is, can I use Kramer's rule to solve this problem? Well, to find out, I need to calculate the value of the determinant of my coefficient matrix. How do you do that?
Down diagonal minus the up
Okay,
diagonal.
3 times 2 minus, which is, okay, it's not 0. So because it's not 0, I can proceed with Kramer's rule. For d sub x, I need to get rid of the 2 and the negative 4. Get rid of them. Replace them with 3 and 8. So instead of 2 and negative 4, I have 3 and 8. What about the y's? Stay the same. Let's calculate this one real quick. Down diagonal
9,
minus the up diagonal,
40,
negative 40. 9 minus negative 40, 49. Now to get the y determinant, I'm going to replace the y column. So instead of a negative 5, 3, I'm going to put the 3, 8. The x column goes back to the x column. Are y'all okay with this replacement process?
no, place of politics, yeah.
Okay. Down
16,
minus up,
negative 12,
16 minus negative 12. Okay, we're not done yet. Okay. X, the value of x is equal to dx divided by d.
what does that mean?
What is dx?
49
49. What is D?
Where'd you get that equation from?
Hey, Kenny, so you remember on the last,
Kramer's rule.
on the last slide where it was all the letters, where it was like,
But isn't this Kramer's rule?
But what is on the top? Okay,
C1 B2 minus C2 B1.
instead of C, they're using actual solution.
that's dx.
Oh,
That's D.
Oh,
That's dy. That's D.
okay.
Okay. Does this reduce? -7/2. 7 goes into 49 7 times. 7 goes into 14 twice. Yes?
Yeah, negative 7.
Okay. Why? Y is dy divided by d. dy is 28. D is still -14. So once you compute that coefficient matrix determinant once, you don't have to do it again. And this is, which means the solution to the system is the point -7/2, -2. And that's just using Kramer's rule. I didn't do all that elimination stuff. I didn't do substitution. I found 3 determinants. I found those 3 determinants, did some division, and I was done.
Why do they not do this?
Okay.
It's a lot longer than substitution.
Yeah,
I feel like there's a whole lot less. writing.
What?
See,
But what if it was 3 equations and 3 unknowns?
Okay, that's different, but this one is only 2 equations.
Right, right. But if we had 3 equations and 3 unknowns,
But-
yeah.
There's no such thing as that.
Yes, there is.
Only if he doesn't like. Well, divide you would be.
Kramer's rule generalizes easily to systems of n equations and n variables. So I could use Kramer's rule to solve a system of 12 equations and 12 unknowns. Could you imagine doing substitution or elimination with 12 equations and 12 unknowns?
I would put random numbers out there that make sense. Yep, y equals 12.
The denominator is the determinant of the coefficient matrix. The numerator is the determinant of the matrix formed by replacing the column corresponding to the variable with the column representing the constants. And that's what I've been saying over and over and over again. So this is what 3 equations and 3 unknowns would look like. This would be for solving for the 3rd variable. Notice this is just the coefficients. A sub 1, 1, A sub 1, 2, A sub 1, 3, right? Just the coefficients. When I'm solving for the 3rd variable, x sub 3, I'm going to replace the 3rd column. So instead of having A sub 1, 3, A sub 2, 3, and A sub 3, 3, I'm going to replace it with B1, B2, B3. This is just general form. If a system of n linear equations and n variables has a coefficient matrix A with a non-zero determinant, then the solution of the system is. So what this is saying is I don't care how many equations and how many unknowns you have. It's going to be each variable matrix divided by the coefficient matrix of the original system. Kramer's rule does not apply when the determinant of the coefficient matrix is 0 because you can't divide by 0. Wait, we're going to use Kramer's rule to solve this. So the first thing I need to do is determine my coefficient determinant. My coefficient determinant is going to include what numbers?
4 minus 5.
Okay.
Now do 4 times 5 minus
4 times -5
minus 3 times
minus
2, negative 6.
is, okay. I have two variables, X and Y. So I need to determine my X determinant. But now we're going to talk columns. And most of the times we've been doing filling up matrices, we've been reading across, right? Let's do columns this time. What's my first column going to be solving for X? 10 and 11.
Oh my gosh, I'm sorry.
What's my second column going to be?
-2, -5.
Okay. Let's compute that determinant. Down diagonal, -50
-22.
minus -22.
-26.
-28.
Yeah, -20.
Okay. I need my Y. First column. 4 and 3. 10, 11. Down diagonal.
4 = 14.
Okay. So X is
-28.
dx over d, which is
-28 over -14. 2. And y is d of y over d, which is 14, which is -1.
so my solution is was that really bad?
Oh, but then you gotta pull over like the first two columns, whatever there's 3.
Yeah.
That's gonna be confusing.
I like
Okay.
everything except for the movie.
And there it is. They've worked it. Is that what we got? Yay. That's the end.